Bonjour tout le monde. Mon nom est Octave Cornéa. Je suis le directeur du Centre de recherche mathématique. Me rends compte that I'm saying this for 3 years and a half now, so maybe you know already. But in any case, we are here for a very important occasion. The lecture of this year's winner of the CRM-Fields-PIMS prize, Professor Murty from Queen's University. And I will start things today by saying a few words about the prize. So this is the most important recognition for research in mathematical sciences in Canada. And it's a fact that Canadian mathematicians congregate around the math institutes. And because the math institutes are means for people to do math together, to interact, to train students. And also there were some prizes. And the CRM-Fields-PIMS prize was launched by the CRM together with the Fields Institute in 1994. And this initiative was joined by the Pacific Institute for Mathematical Sciences by PIMS as an equal partner in 2005. So we are now at the 20th prize ceremony or lecture in this new formula of the prize. And I had also to say that the prize comes with a medal, which unfortunately I don't have around, but will be soon sent to, and with a monetary award, which I also don't have, but I was told that it will be transferred into his account at some moment. And and also I had more things to say about Ram, but I prefer to pass the microphone to Professor Chantal David from Concordia University, who will tell you more things about the prize winner.
Thank you very much. So it's my pleasure to introduce the recipient of the prize, as the actor said, which is given for, it's a premium Canadian award given for exceptional research achievement in the mathematical science. So Ram completed his PhD at MIT under the supervision of Harold Tark in 1980, and was then a professor at McGill for 1982 to 1996. And he's now professor, Queen's Research Chair, and Douglas Distinguished University Professor at Queen's University. Ram works in number theory, has published more than 280 papers about every subject in number theory, combining algebraic and analytic techniques. In addition to his exceptional research, Ram is also an exceptional mentor for a generation, I would say several generations of young number theorists. Some of them are not young anymore, you know. He has mentored about 40 postdoc fellows and 50 graduate students in his career, a truly impressive record. So I have the privilege to be one of former student, Ram, a former student, and I think I can speak for all former students and postdoc, how grateful I am for his time and his generosity with his mathematical ideas, which years after I would remember things that you told me and, oh, I understand, oh, it gives me this other idea. So thank you very much in my name and in the name of all the other students who are listening or not. So today Ram will tell us about L-function, a fundamental object in number theory in which he had contributed many significant results over the last years. Thank you.
Thank you very much, Octavia and Chantal. Thank you for that nice introduction. And it's a pleasure to see many of the people that I've worked with in the past. And I see the founding father of the Sigma number theory group in Montreal here, Professor Claude Levesque. So I'm very happy to see everyone and be here. It's like coming back home. So today I want to give you a snapshot of what is an L function and give you a brief historical tour first, and then try to come to the forefront of current research at the end of the talk. So what is an L function? Well, a zeta or L function is essentially a Dirichlet series attached to a multiplicative arithmetical function. So the question of what is an L function is intimately related to the question of what is a multiplicative function. I'm going to give more details about this in a second, but by studying the analytic properties of these series, one deduces information about the arithmetical function. So since I have the blackboard at my disposal, I'm just wondering where the piece of chalk is, but maybe there isn't any. Oh, it's here. Okay. So essentially, you should think of an L series as some sort of Dirichlet series, a sub n over n to the s, where a sub n is a multiplicative function. So that means a sub mn is equal to a sub m times a sub n whenever m and n are relatively prime. So this is a basic understanding of an L function in this kind of rather naive perspective. So often this L function contains some deep information about the distribution of prime numbers and can be considered as a global object. And because it is a multiplicative function, it can be decomposed as a product of local objects. And so in many ways, the L function contains within it the local global principle. So in a profound way, the L function encapsulates a local global principle for the L function. I'm sorry about the bottom part of this slide, but I'm sure you can infer what that says. So let me begin with the person who first somehow introduced the concept of an L function or a zeta function. It goes back to Euler. A century before Riemann had introduced his zeta function, Euler had studied what's called the zeta function now, but he didn't study it as a function of a complex variable, but rather as a function of a real variable. And beginning with the Dirichlet series summation 1 over n to the s, and noticing that every natural number can be written as a product of prime numbers in a unique fashion, he was able to establish what's called an Euler product. So that means the series can actually be written as an infinite product over prime numbers. And this kind of connection encapsulates the unique factorization theorem of the natural numbers. So this allowed him to give a new proof of the infinitude of primes. It looks like a more complicated proof than Euclid's, but still, it's a very powerful idea because it admits a generalization. If you take the limit as s goes to 1 of the Dirichlet series, we all know that summation 1 over n diverges. Therefore, that shoots off to infinity, and you can't have finitely many primes because otherwise it'll converge to a finite number. So basically, that's Euler's proof, and it's interesting to note that this particular proof of the infinitude of primes is what Dirichlet picks up to show there are infinitely many primes in arithmetic progressions. So this proof actually generalizes. Euclid's proof doesn't generalize very well. So you do need the object of a Dirichlet series, this local global principle idea, in order to make things work. So this is what I just said. So Euler also solved what's called the Basel problem, which was to evaluate explicitly zeta 2. And most of you probably know that zeta 2 converges to pi squared over 6. And more generally, zeta 2k is a rational multiple of pi to the 2k. So he managed to calculate these special values where b sub k is the kth Bernoulli number. And of course, the question of what the special values are for odd arguments is essentially still open, although we know some information about that. So let me say a few words about Gauss. Gauss started the game in some sense, tried to make a precise conjecture about the distribution of prime numbers. As a teenager, he made this conjecture that the number of primes up to x should be asymptotic to what's called a logarithmic integral. So in some sense, this is a better approximation than x over log x. And so he conjectured that that was the behavior. And we call the statement pi x is asymptotic to logarithmic integral as the prime number theorem, or PNT for short. And after his conjecture, there was quite a bit of work, notably due to Chebotarev, who showed that there were constants a and b such that pi of x grows like x over log x. But Chebotarev tried very hard using elementary methods to show that the prime number theorem was true. And he showed finally that if the limit exists, it's actually 1. But he couldn't prove that the limit exists. So it's prime number theorem required deeper methods from complex analysis in order to resolve it. Now, so now we come to Riemann after the work of Chebotarev. Riemann had shown that in order to prove the prime number theorem, you actually have to think about the zeta function as a function of a complex variable. There's no other way of doing this. And he, in his paper, famous paper, 1859 paper, it's only 8 pages or something, he showed that the zeta function can be extended as an analytic function to the entire complex plane, and showed that it satisfies a functional equation relating the value at s to 1 minus s. So there's kind of remarkable symmetry between this function. And he gave a heuristic derivation of an explicit formula for the number of primes up to x. And this formula involved the zeros of the Riemann zeta function. So the famous zeros of the zeta function, which are in what's called the critical region. But he couldn't prove it. He laid the groundwork, and the final steps were given by Hadamard and de la Vallée-Poussin. Independently, they gave a rigorous treatment of Riemann's work, and finally showed that the prime number theorem follows from the fact that the Riemann zeta function has no zeros on the line real s equals 1. It was only much later that this was shown to be equivalent to the prime number theorem. So this is Hadamard and de la Vallée-Poussin. And in the 1859 paper, of course, Riemann makes this famous hypothesis that the zeros of the zeta function inside this region, critical region between a real part lying between 0 and 1, any zero has to be on the central line of symmetry, which is a real part s equal to half. And of course, as you all know, this problem is still open. Now, in the 1920s and the 1930s, Norbert Wiener tried to look at this very seriously and showed that, in essence, the prime number theorem is equivalent to the statement that the Riemann zeta function doesn't have any zeros on the line real s equals 1. So the easiest ways to understand the work of Hadamard and de la Vallée-Poussin is through the Wiener-Ikehara Tauberian theorem, proved in the 1930s. Usually this theorem is derived using fair kernel, and recently I have a paper where we give a simpler proof using a device due to Newman. And I think I'll just flash this and just show that essentially anytime you have an analytic continuation of the series with a pole of a certain order and non-vanishing of the residue, immediately you get an asymptotic formula. And from this, you can derive many, many theorems in analytic number theory. The proof of the prime number theorem can be deduced from the Tauberian theorem very easily. If you go back to the factorization that Euler had of the zeta function as an infinite product over prime numbers, you'll see that by taking logs of both sides, you get a Dirichlet series again with this function called the von Mangold function. I think this maybe not doesn't work. Okay. This von Mangold function, which is essentially supported on the prime numbers or prime powers, and using the fact that the zeta function doesn't vanish on the line 1, you can apply the Tauberian theorem very quickly and immediately deduce the asymptotic formula as you would want it, which is psi x is asymptotic to x. And from that, you can do a partial summation trick to get back the theorem that pi of x is asymptotic to x over log x. So this is basically the proof, but it took almost 50 years after Riemann to sort all this out. And for primes in arithmetic progressions, we owe it to Dirichlet. It's interesting to note that Dirichlet L-functions were introduced before the Riemann zeta function was introduced, weird as it sounds. But as again, the study of these L-functions that Dirichlet had introduced was essentially the function of a real variable as opposed to a function of a complex variable. And that's why Dirichlet was only able to show infinitude, but he wasn't able to count them. Yeah. So in the process of trying to show that there were infinitely many primes in an arithmetic progression, you had Dirichlet characters, which I think essentially we owe the discovery of character theory, theory of finite groups, to this particular problem. So associated to a character, you have this Dirichlet series LS chi, which again is a multiplicative function, as I outlined here, and it also has an Euler product. So here we have a similarity between the Riemann zeta function and these Dirichlet L-functions. A series is again a product over prime numbers. And Dirichlet discovered that these characters satisfy an orthogonality relation. And using this orthogonality relation, he was able to show that, well, you can now apply the idea of the Tauberian theorem by taking a clever combination of L prime S chi over LS chi to sift out primes in that progression using the orthogonality property. And the application of the Tauberian theorem immediately gives you the asymptotic formula counting function for the number of primes in a fixed arithmetic progression. Again, the key idea in the Dirichlet's proof, where there's just simply infinitude, is the fact that L1 chi is not zero. And the key idea here is that you need to get LS chi not zero on the entire real line in order to get the asymptotic formula. So in order to prove that, the simplest proof is actually using Dedekind's zeta function. So all of this activity in the last part of the 19th century motivated many people to discover new generalizations of the Riemann zeta function. And one of them happens to be the Dedekind zeta function. So what is that? Well, here's Richard Dedekind. If you take an algebraic number field and you look at all the numbers in that field that satisfy a monic polynomial equation with integer coefficients, those are called integers. And the collection, the totality of all such algebraic integers in that field forms a ring. And beautiful theorem is that every ideal in that ring can be factored as a product of prime ideals. So the generalization of the unique factorization theorem to the algebraic setting is very beautiful and due to Dedekind. And in fact, Dedekind domains are characterized by the fact that the ring has this unique factorization property. So you can now define what's called the Dedekind zeta function, which is going to be the series given by the norms of the ideals to the power S. And again, by the unique factorization theorem that Dedekind had discovered, you can write an Euler product. So it's exactly similar to the Riemann zeta case or the Dirichlet L function case, that you have a series, a Dirichlet series being decomposed as an Euler product or product over primes. And again, by applying the methods of Hadamard and de la Vallée-Poussin, you find that the zeta function of Dedekind extends analytically to real S equals 1 and doesn't vanish there. Applying the Tauberian theorem, you get what's called the prime ideal theorem instead of the prime number theorem. How many prime ideals are there with norm less than x? And it's again, it's asymptotic to x. I think it's probably Landau. Who did it?
I don't know the answer.
I think it must be Landau. Yeah, it must be Landau. Yeah, because you see, you need to show that the Dedekind zeta function doesn't vanish, and you need some sort of non-negativity trick. And I'm just guessing it's Landau's. Yeah. So Hecke showed in 1918 that the Dedekind zeta function, like the Riemann zeta function, extends to the entire complex plane, satisfies a suitable functional equation relating the values of at S to 1 minus S. And the interesting thing is Tate's thesis is a Fourier analytic proof of Hecke's 1918 theorem. I like this joke. There's nothing new in Tate's thesis. But there's everything new in Tate's thesis. You see, this is, I keep telling my students this, that when they come up with new proofs of old theorems, nothing to frown about. It could be potentially dynamic. That's exactly what happened with Tate's thesis. Tate's thesis is a remarkable and ingenious idea, which actually generalizes in the Langlands program. So the very complicated proof that Hecke had given is made so transparent and obvious once you have the Fourier analytic perspective. That's essentially Tate's thesis. So the the functional equation relating S to 1 minus S is reinterpreted as a consequence of Fourier duality. Now, in the context of the same period, historical period, we have what's called the Ramanujan zeta function. See, zeta functions and L functions we've discussed so far are to be thought of as one-dimensional. And there are higher dimensional versions of this. The first version, which is two-dimensional, was provided by Ramanujan in 1916. He introduced his famous tau function, which is defined as this coefficient of the power series. And he made these conjectures that the tau function is a multiplicative function. That's a conjecture that he made. And the fact that the tau function satisfies some sort of second-order recurrence relation. And finally, the third conjecture that tau of p is less than 2 times p to the 11 halves. And all of these boil down to the fact that you have a Dirichlet series in your hands, you have a functional equation in your hands, and you have an Euler product in your hands. So basically, it fits neatly into the theme of the discussion that I started out with. In general, what is an L function? It's essentially a Dirichlet series with the coefficients being given by some sort of multiplicative property. So it fits neatly into that scheme of things. Now, in the context of Ramanujan's work, the first two conjectures were proved by Mordell shortly after Ramanujan made the conjectures. And the third one was, as practically all of you know, is a famous conjecture, consequence of the Weil conjectures, proved by Deligne in 1974, for which he was awarded the Fields Medal. Now, Mordell, interestingly enough, seems to have missed an opportunity to develop what is now called Hecke theory, since his proof actually generalizes to all modular forms. Now, if I had to put my finger on a tragic hero of the 20th century number theory, it has to be Mordell, because he came up with all the brilliant ideas that transformed 20th century number theory, but he didn't develop them. You know, he could have developed them. It was a kind of a very interesting situation. So in that context, you see this particular function of Ramanujan held a key to a larger theory, which we would call the Hecke theory. Now, in the Dedekind eta function had already been studied by Dedekind earlier, before Ramanujan. And if you notice, if you take the 24th power of the eta function, you get the Ramanujan function. The eta function was known to satisfy some sort of modular functional equations. And it's a complicated modular relation, but I won't go into it. Let me just say, just flash it in case anyone is interested. I can give you these slides and you have all the details. There are these subtle things called the Dedekind sums that enter into this formula. And by taking the 24th power, which Ramanujan was doing, all these 24th roots of unity disappear. So the complicated stuff disappears and you get a nice theorem. So now the interesting thing is that the eta function had been studied, and various powers of the eta function had been studied by many people. Euler's pentagonal number is basically, if you take the eta function without the q to the 1 over 24th factor and just consider this as a power series, you can actually develop the power series, and you can get these coefficients, -1 to the k, and the exponents are going to be quadratic numbers of this, what are called triangular numbers. Pentagonal numbers. And so because they enumerate these configurations illustrated here. Now, a similar idea was the generalization of that. Jacobi's theorem, his famous triple product identity, allows you to write down modifications of that product thing into, again, an infinite product as an infinite series. And Jacobi proved in his 1828 paper that when you take the cube of the eta function and drop that the initial part, you get a very nice expansion again with I don't think this works. Okay, with coefficients being again quadratic, but you have an explicit statement for the coefficient being -1 to the k times 2k plus 1. Now this is essentially the explicit expansion of the cube of the Dedekind eta function. So here we had Euler's pentagonal theorem, which gives you the eta function, the coefficients in the eta function without the q to the 1 over 24. Here you have the cube of the eta function essentially, and the question arises whether there are more such things to study. And Gauss discovered a few more. If you look at essentially products of this type, you take various quotients and products, he managed to get similar identities. And the question is, are there more? And Winquist as late as 1969, and Dyson as late as 1972 discovered two more. They discovered that the 10th power also satisfies something similar, and you can write down all the coefficients explicitly. And this motivated Freeman Dyson to make the discovery for the 24th power. And here's Freeman Dyson. He says that he started noticing something, but he missed an opportunity. So let me explain this in his own words. He says, I started life as a number theorist during my undergraduate days at Cambridge. I sat at the feet of the already legendary figure G.H. Hardy. It was clear even to an undergraduate in those days that number theory in the style of Hardy and Ramanujan was old-fashioned. I don't agree with that, by the way. And did not have the great and glorious future ahead of it. Indeed, Hardy, in a published lecture on the tau function of Ramanujan, had himself described this subject as one of the backwaters of mathematics. And the tau function defined is the coefficient of this modular form that I had flashed on the earlier slide. Well, he writes, that long after I became a physicist, I remained it retained a sentimental attachment to the tau function, and as a relief from the serious business of physics, I would, from time to time, go back to Ramanujan's papers and meditate on the many intriguing problems that he left unsolved. So 4 years ago, during one of these holidays from physics, I found a new formula for the tau function so elegant, it's rather surprising that Ramanujan didn't think of it himself. The formula is that tau n is given by this kind of sum function where these a, b, c, d, e satisfy these equations. The sum is 0. The sum of the squares is 10 times n, and they have to satisfy these congruences. So it's a very nice formula. So Dyson goes on and says, well, afterwards, referring to the work of MacDonald, which happened only in the 1970s, he says, pursuing these ideas further by my pedestrian methods, I found that there exist formulas of the same degree and elegance as for d equals 3, 8, 10, 14, 15, 21, 24, 26, 28, 35, 36. And then he says, well, d equals 3 was Jacobi's, d equals 8 was Klein and Fricka, d equals 14 was 26 is Atkin. There I stopped. I stared a little for a while, this queer list of numbers. As I was for the time being a number theorist, they made no sense to me. My mind was, this is interesting, my mind was so well compartmentalized that I did not remember that I had met these same numbers many times in my life as a physicist. If the numbers had appeared in the context of a problem in physics, I would have certainly recognized them as the dimensions of the finite dimensional simple Lie algebras, except for 26. Why 26 is there, I still don't know. The others all correspond to simple algebras, A1, A2, B2, G2, A3, B3, A4, D4, A5, B4, and so on. And for example, D equals 24 corresponds to the algebra A4. And the structure of the formula 2 that I had flashed on the previous, you can see the root system of A4. So I missed an opportunity of discovering a deeper connection between modular forms and Lie algebras, simply because his mind was compartmentalized. The physicist Dyson was not speaking to the number theorist Dyson. So this is a case of mathematical schizophrenia. Now, let me just give you a crash description of this stuff, because it's important. If you have a vector alpha, you have a hyperplane orthogonal to that vector, and you consider all the reflections of these vectors with respect to that hyperplane. And any vector v can then be written as a vector x and a vector in the hyperplane. So you can write it down in that way and then calculate what the reflection should be. And essentially, this is how, the interesting thing about the theory of root systems is an elegant chapter in mathematics that came by trying to classify simple Lie algebras. And it's so beautiful that it has these connections to number theory. So you just axiomatize the whole thing. You don't need to even talk about Lie algebras. You can just axiomatize classical vectors in Euclidean space satisfying various properties. So you take a root system, a bunch of vectors. They have to have 3 properties. It spans V. If alpha is in this root system, then no other integer multiple except minus that is in the root system. And then if alpha and beta are roots, then 2 alpha beta over alpha alpha, the inner products is an integer, and the reflection in the hyperplane is a root. That's it. Once you have these axioms, then you then prove a beautiful theorem in root systems that says there's a fundamental root system which every root can be written as a non-negative linear combination of these fundamental roots, like a unique factorization theorem. And then you have these positive roots and negative roots, and then to every simple Lie algebra, and every Cartan subalgebra, which is basically a abelian subalgebra, you can decompose the Lie algebra as a direct sum of one-dimensional spaces because the abelian stuff is acting on the non-abelian Lie algebra and will decompose into one-dimensional spaces. And these one-dimensional things are the characters. And once you have this concept, then you can state MacDonald's identities. You take a simple complex Lie algebra, take delta, its set of roots. You take some of the positive roots, and then you form these lattice, capital M, which is just the span of these roots. And then you define this function d of mu, which is just a product over all the roots. And the MacDonald identity is that if you take the dth power of the eta function, the coefficient is exactly that. That's it. That's a beautiful way of saying MacDonald identities without too much background in Lie algebras. So beautiful idea. And yeah, I mean this is how it came about exactly. Yeah, it's good to know many things, and it's good to have people talking to each other. I would say, yeah, that's exactly the moral of the story. And so any dth power. Now, if you go back, you can see that you can interpret the coefficients of these dth powers as these inner products of inner products coming from the root system. So in other words, MacDonald's identity gives an explicit expansion of the dth power of the eta function where d is the dimension of a simple Lie algebra. Now, by the way, I still don't know the answer to that question, why 26 was there. That's a good question, and I've asked some experts, and they seem not to know either. So if there's Lie theorists in the room, maybe it's a good question to think about. Now, in the context of the Ramanujan tau function, Hecke had developed the theory almost 20 years after Ramanujan. And Hecke's theory generalizes the Ramanujan example, and I'm just going to flash this because it's a little technical. You consider modular forms in the upper half plane, functions that transform according to SL2Z, or a certain subgroup of SL2Z according to the modular relation. And then you write down a Fourier expansion for it. And then what Hecke proved was to each modular form, he attached a Dirichlet series and showed that it extends analytically to the entire complex plane and satisfies a suitable functional equation. But the question of Euler products was a little harder. And so to admit an Euler product, it had to be an eigenfunction for a sequence of linear operators, which are now called Hecke operators. So this initiated a theory of two-dimensional L-series, which was later generalized by the Langlands program. So in other words, the two-dimensional L function that Ramanujan had discovered was developed, as I say, rather late, 20 years after Ramanujan, but it was finally completed by Hecke by the 1940s. And as I mentioned at the very end, the question of what does it mean for something to be an eigenfunction of Hecke operators? What are Hecke operators, and why is it that only certain L functions had Euler products and not all of these L functions had Euler products? So this is the question that in some sense is answered very nicely by the Langlands program. Now, in the context of, again, the same historical development, parallel to Hecke was the work of Emil Artin. Now, by the way, I'm told that Artin and Hecke were both professors at the University of Hamburg. And there's even one story that says that their offices were next to each other. And they shared a wall on which, of course, there was a blackboard. And it seems that when Hecke was working on his L-series, Artin was working on his L-series on the other side of the wall. And the reciprocity law that Artin was like Alice through the looking glass. The reciprocity law that Artin was conjecturing, the special case was being proved by Hecke on the other side. It's an interesting story. So in 1923, Artin introduced his famous non-abelian L-series. So you go back to these Galois extensions with the Galois group G, and to each prime ideal, you can associate a certain element in the Galois group called the Frobenius element. And given a representation of the Galois group, you can associate now an Artin an L-series. Now notice, with Artin, you define the L-series as an Euler product. You didn't define it as an L-series like Ramanujan was doing or what Hecke was doing, but you actually define the L-series as an Euler product to start with. So the coefficients that come out are multiplicative functions automatically. So Artin conjectured that each of these L-series extends to the entire complex plane, and it's entire if rho is irreducible and non-trivial. This conjecture is still open, but if rho is one-dimensional, Artin proved this conjecture, and this is often called Artin's reciprocity law. And Langlands, Tunnel, and Kare have shown that if rho is two-dimensional and solvable, this conjecture is true. Now, the general Langlands program is essentially motivated by trying to prove Artin's conjecture. So this is an interesting motivation for much of the Langlands program. Now, in the context of trying to prove Artin's conjecture, many interesting developments took place in the 1940s. One of the most important is Brouwer induction theorem, which says that any character of a finite group is an integer linear combination of inductions of one-dimensional characters of certain subgroups called elementary subgroups. And these elementary subgroups are nilpotent groups, and using Artin's reciprocity law and some functorial properties, you can show that these L-series are all meromorphic, and then you can use the fact that Hecke had shown all these L-series don't vanish on the line real S equals 1, and because the Artin L-series has been written as a quotient of Hecke L-series, you now deduce the Artin L-series are also non-vanishing on real S equals 1, and immediately you can apply the Tauberian theorem, and you get a super generalization of the Dirichlet theorem in primes and progressions, which is often called the Chebotarev density theorem, which tells you these Frobenius Artins, these symbols, the Frobenius of P are uniformly distributed in the group G as the prime ideal P varies. So the non-vanishing of L functions provides the solution to concrete number theory problems. So I hope I've convinced you so far that there's this interplay between Dirichlet series, Euler products, and somehow having a non-vanishing theorem of the L series allows you to deduce some profound property of the prime numbers. And this goes on. So here are the examples discussed so far. So you have on the one hand distribution of primes, and on the other hand, the Riemann zeta function doesn't vanish on the line rho. Then you have the distribution of primes in arithmetic progressions, and then that's equivalent to the L function not vanishing on the line rho. And then you have the distribution of prime ideals, that's equivalent to the Dedekind zeta function not vanishing. Then you have the distribution of Frobenius elements in conjugacy classes, the Chebotarev density theorem, and that's equivalent to the Artin L function not vanishing on the line. So every time you need some property of prime numbers, you move into the world of L series and then show the non-vanishing theorem, and then lo and behold, out pops this deep property that you're looking for. That's been the theme of analytic number theory. Each L function contains a sacred secret about prime numbers. So in that sense, they are divine. Now, this is where in the 1960s, Langlands was studying these repertoire of results. And in 68, he proposed a new program generalizing the work of Hecke. So Hecke's work was a motivation for him. And he was wondering, why did you need to introduce these Hecke operators? So why not define your L-series as an Euler product like Artin did, even in the Hecke context. And that's what he was doing. So he introduced what are now called automorphic L-functions, and he wrote this very short but very difficult book to read called Euler products. They were his Yale lectures. I think it's not even more than 40 pages long, but it's very difficult to read. And the title of the book is Euler products. So there he's basically showing that these L functions that he's introduced are entire. They satisfy suitable functional equation, and then predicted that the Artin L-series are among them. So in other words, he proved, I'm oversimplifying a little bit. He proved, meaning not himself, but his school had proved. I mean, basically, Godemar-Jacquet, Jacquet and Langlands, and so on. So all these people in his school had proved that these automorphic L functions are entire and they satisfy a suitable functional equation. And he conjectured that the Artin L series are in the class, but that's has not been proved yet. So in this way, Artin's conjecture would be proved via reciprocity law. And building on the earlier work of Gelfand, Fomin, Harishchandra, he viewed modular forms from a representation theory perspective, and his innovation was to introduce the Adelic approach and generalized method of Tate's thesis. So Tate's thesis was his template in building up the Langlands program. So because he had that Fourier analytic perspective, he would use that as the template to build a general program for GLN. So the assertion that an Artin L-series is automorphic is often referred to as a strong Artin conjecture. So Artin's conjecture was just that these L-series, these non-abelian L-series are entire. But what Langlands is saying is they're not only entire, but they are automorphic L functions. And that's a stronger statement. And in fact, the proof of Fermat's last theorem, as Henri would say, is a statement of a certain reciprocity law that all elliptic curves are modular. That's a kind of a reciprocity law. So this is again the beginning of a big picture. So from modular forms to automorphic representations, I don't want to belabor this too much, simply in the interest of time, but essentially the idea is to associate some symmetric space generalization of the upper half plane and try to reinterpret modular forms from a group theoretic context. So I'll just flash this a little bit quickly and reinterpret all the classical theory of modular forms and Moss forms group theoretically, which you can do, and find that you can formulate a group theoretic interpretation of all of this, and then shift to the Adel ring. So what is the Adel ring? Well, the field of real numbers is the completion of Q, ordinary rational numbers, with respect to the ordinary metric. Ordinary metric, the distance between x and y, is just the absolute value of x minus y. But as you all know, there are p-adic metrics, one for each prime p. You can endow the rational numbers with a p-adic metric. Essentially, you take a rational number, you take the power of p that divides it, and then you say the length of that particular rational number is p to the minus that power. And that gives rise to a particular metric called a p-adic metric. And essentially, a famous theorem of Ostrowski says that these are the only ways to complete the rational numbers. So in some sense, the p-adic topologies and the ordinary topologies are the only topologies that you can kind of completions with respect to these metrics that you can have. So according to Artin, one should look at all these completions in the same way. So in other words, when we teach classical analysis, we're essentially teaching analysis of the real line. But you should be really teaching p-adic analysis on par with the classical analysis, one for each prime p. And therefore, you would build up a number theory in this Adelic perspective. By the way, this is actually very useful, even in probabilistic number theory, when you want to interpret, especially L series coming from Euler products, you want to interpret somehow the Euler factors as independent random variables, one for each prime p. So that perspective, this new perspective is already proving to be very fruitful in classical analytic number theory. So in this Adelic context, you have a Haar measure, And Tate's thesis is the Fourier duality of this ring is at the heart of the functional equation for the Dedekind zeta function. So why should we study Adeles? Well, if you want to determine all the characters of the rational numbers, they're parametrized by Adeles. The character theory of the rational numbers is actually the Adele ring. So the work of Dirichlet, Hecke fits neatly into this framework, and this is what John Tate did in his famous PhD thesis. The Adele framework works well for the Langlands program too, and L-series attached to automorphic representations have been continued analytically to the entire complex plane and satisfy a functional equation. In all these cases, the coefficients of the associated Dirichlet series are multiplicative functions of a single variable. So you see here, these are functions of a single variable. This is a multiplicative function of a single variable. Therefore, it's natural to ask, should we study multiplicative functions of several variables? And that's what we're going to do now. So in this context, there's Selberg class. Another perspective of Selberg is to introduce zeta functions, which he had done, which satisfied the Euler product criterion that he had. So his Euler product is a little bit different from Langlands. And so Selberg tried to axiomatize the properties of Dirichlet series with Euler products in his famous paper. And this particular class of functions is called the Selberg class. And Selberg made famous conjectures about some sort of unique factorization theorem holds for this class. He tried to define the building blocks of these things, he called them primitive functions. And he conjectured that he showed actually that every function can be written as a product of primitive functions, but he couldn't prove that it's unique. It's still open, it's an open question. And he made these conjectures from which it follows, the unique factorization theorem follows some sort of Rankin-Selberg property of these L-series. Now, in 1994, I showed that Selberg's conjectures actually imply the strong Artin conjecture. In other words, the Artin holomorphic conjecture is true, and every Artin L-series comes from an automorphic representation if you have the Selberg conjecture. So there's something about the Selberg world, and there's something about the Artin world, and there's something about the Langlands world that somehow there's some interesting intersection. So far, as I said, we've studied multiplicative functions of single variable. And in the follow-up paper, Selberg alludes to a certain theory of multiplicative functions of several variables. And what Selberg was not aware of was that this had actually been studied in 1928 by Vaidyanatha, who had developed a theory of multiplicative functions of several variables where you think about functions of k arguments. And in that context, what Vaidyanatha does is he essentially redoes elementary number theory from this perspective and develops this Mobius inversion formula and all sorts of wonderful things. And he says that a function is multiplicative. I'm sorry, this last thing is here. It's a very important property. Basically, I should write this down. So okay for time. So here, the property is f of m1, m2, mk times f of n1 and k should be equal to f of m1, n1, mk, and k, provided that essentially the GCD of m1, mk, n1, mk, the GCD is 1. In other words, the m's should have nothing to do with the n's, and that's his generalization. So many people try to give the generalization of a multiplicative function of several variables, and you have tons of definitions in the literature, but there's something which is we call the right one. And the right one seems to be this one, and this is the one that also Selberg hits upon in his paper in 1972. So example, the Ramanujan sum, which is defined in this fashion, is a function of two variables, q and n. And it is a multiplicative function of two variables if you take the Vaidyanatha-Swamy definition. But it is not a multiplicative function in the classical sense of the word. If you fix, for example, if you fix q and think of it as a function of n, it's not a multiplicative function. And if you fix n and you think of it as a function of q, it is. But you need this new definition. And these Ramanujan sums have some sort of orthogonality property, which Carmichael had shown in 1932. And in joint work with Sneha Chobe and Shivani Goel, we studied triple convolutions of these Ramanujan sums. So there is kind of an orthogonality principle again with these Ramanujan sums for triple convolutions. And our paper, the first paper, was rather complicated, examining lots and lots of cases. And finally, we found a better, with Shivani Goel, who was Sneha's student, we found a simpler way of doing this using this general theory of multiplicative functions of several variables. So in this work, we had extended this to the following theorem. So if you take any bunch of numbers a1 to ak and consider this multiple convolution of Ramanujan sums, then you get this limit f of q1 to qk exists, and this limit equals this crazy combination. What is this function g? This function g is 1 or 0 if 4 has a solution. What is that? So this is a kind of interesting scenario. So essentially, it's the Chinese remainder theorem, x equals a1 mod d1, x equals ak mod dk. In the Chinese remainder theorem, normally you take d1 to dk mutually coprime. But don't do that. Take them arbitrary. Then it still, whether the system has a solution or not, turns out to be a multiplicative function of d1 to dk. That's the big deal. And so that goes and gets itself stuck in this limit formula, and everything is multiplicative in the sense of Vaidyanatha-Swamy. So we applied this method to study the asymptotic behavior of moments of Ramanujan sums. And this particular question was brought to my attention by this student, Shivani Goel, who found a mistake in a paper of Arindam Roy and Robles, where they had incorrectly calculated this limit. So in joint work, we finally corrected their paper. The paper shows an asymptotic formula for this particular thing, y times x to the k times a polynomial in log x. So in the Robles-Roy paper, this polynomial in log x isn't there. So they missed it. And it has a lot to do with Dirichlet series of several variables. So we had to use a theorem for multiplicative functions of several variables, Tauberian theorem due to Breteche, which generalizes the Tauberian theorem that I had talked about earlier. And I'll just flash it. So if you have a function of several variables, you have to check that this function extends analytically to larger domains and satisfies various properties, which I will not discuss in the interest of time. And lo and behold, when you have this, you get what's called this Tauberian theorem, which gives you an asymptotic formula for the summatory function of the function of several variables in terms of these exponents. And now notice that there's a power of log x in the argument. So this log x comes from by analyzing the Dirichlet series of several variables that you have. And in our context, in the context that I had just flashed in the earlier thing, the Dirichlet series that enters the picture for the moments of the Ramanujan sum problem factors neatly as a product of classical zeta functions. And then you're able to check all the conditions of the Breteche Tauberian theorem and deduce the extra power of log x that was supposed to be there. So thank you for your attention. Life, I say, is for discovery and self-discovery. There are higher levels to explore. May the Himalayan peaks inspire our minds to greater heights. Thank you for your attention.
Thank you very much for a great talk. Are there any questions for the speaker?
Yes.
You mentioned the strong Artin conjecture. if I assume the weak Artin conjecture for all Artin L-functions, does it imply the strong one?
No. So the weak Artin conjecture is just holomorphic? Does it imply the strong Art? No, it won't, because even in the case of two-dimensional things, you know, there's this converse theorem of Weil, which says you need twists by all the Dirichlet characters. And so how will I identify, oh, those will then, oh, so if you assume them in this, for all the twists also,
Then you get holomorphic.
you get holomorphic, but you need the twists. And so now there's a general converse theorem, you know, for n-dimensional representation, you need to twist by automorphic representations of lower levels. And so the question is, if all of those are, they would be Artin L-series. So in philosophically, the answer is yes, philosophically.
Okay.
But you know, we all know as mathematicians that philosophically it's great to prove theorems, but mathematically you have to get down and do the dirty work and figure out exactly what is involved, make a great thesis problem.
Like for in Weyl's converse theorem, what if you add the, you know, all but finitely many or half of the character? I don't
Yeah,
even
no,
know
no,
if
no,
you can-
it's been done. It's done for that.
been done?
No, well, that's been done. You see, you're right. In Weyl's classical paper, he says all the twists, okay? But then there's a paper by Michael Razar, and I think Razar and Goldstein or somebody, Razar and somebody. They actually said that if you had a function with a certain conductor, you know, and you're trying to show it comes from modular form on gamma naught n, you can twist by Dirichlet characters up to mod n. So there is a kind of a more quantitative finitely many theorem. I don't know if that's been done for higher level automorphic forms. Henri has a question. I'm glad you asked. That's exactly what I'm alluding to. I think there is probably some sort of Langlands program that has to be done for some sort of multiple, you know, multivariable L functions, multivariable L. But he was still thinking of one variable, right? So is it possible, for example, he was defining his L function using representation theory. Is it possible if you took different, you know, you can think of n to the s as a kind of a quasi-character, right? The n to the s is a quasi-character. So if I took different quasi-characters, you know, and instead of taking the same s, would I get different L functions, which have several variables, and what are those like? So that's one idea behind what I was suggesting.
And are these receiving modules or the larger?
Well, you're the expert. No, no, I don't know. I don't know. So Dana has a question. Yeah.
Probably not. But this week there was an article in Le Monde announcing that a big chunk of the Langlands was done by a team of researchers headed by Dennis Gaskell. And so this is the geometric Langlands.
Yeah, yeah.
So the L functions, they have,
Yeah, yeah, in the geometric Langlands, yes, yeah. Yes, it's yeah, so that's a reciprocity law. I mean, I think AL probably knows more about this, but it's a reciprocity law at the local level. It's the local at QP. That's as far as I understand. So it is a part of the Langlands program. You see, when I said the global reciprocity law, well, there's a local reciprocity law. So somehow the Galois representation must correspond to kind of a local automorphic representation. That's the local reciprocity law. And that's what's been proved. As I said, I'm not the expert on that. But that's, if I understand correctly, that's what's been proved. For GLN, not GL2. For GLN.
Well, thanks again for a great lecture.